Okay, so hi everyone. In this video, we are going to discuss about undirected na graphs. So undirected na graphs are graphs in which edges do not have any direction. So the edges indicate a two-way relationship in that each edge can be traversed in both directions. So we can see here a graph G, and it has nodes or vertices A, B, C, D, and E, and some vertices are connected with each other, like A and B, A and D, B and D, D and E, B and E, and C and E. So let's focus on this edge that connects A and B. So since this is an undirected na graph, so we can say that there is a two-way relationship between A and B. So you can traverse from A to B and B to A and vice versa. Okay, so also two vertices U and V in an undirected na graph G are called adjacent or neighbors in G if there is an edge E between U and V. So let's say this one. Let's focus on vertex A. So vertex A is connected or has an edge between B as well as D. So we can then say that A and B and A and D are adjacent with each other. Okay, so what about the vertex B? So vertex B is connected with A, with D, as well as E. So we can say that B and A, B and D, and B and E are adjacent with one another. Or we can say that A, D, and E are neighbors of B. Okay, what about for C? C is only connected with E. And we can then say that C and E are adjacent. Okay, and E is a neighbor of C, or that C is a neighbor of A. So what about D? So for vertex D, there is a connection between A, B, and E. So we can then say that D and A, B and D, and D and E are adjacent or neighbors. Okay. And what about for the vertex E? E is connected with D, with B, and C. So we can say that E is adjacent to C, B, and D, and vice versa. Or we can say that D, B, and C are neighbors of E. So in the previous slides, we have discussed that um, if two vertices are connected, or if there is an edge between two vertices, we can call them adjacent. And such an edge that connects those two vertices, we call that we say that such an edge is called an indecent with the vertices that it connects. Okay, so for example, here we have vertices A and B, which is connected by edge 1. So we can then say that edge 1 is incident with A and incident with B, since this edge is connecting these two vertices. Okay, again, such an edge E is called indecent with the vertices U and V, and E is said to connect U and V. So since these two are connected, so this edge is called indecent to A and B, and this A and B are adjacent. Okay, and then let's say we have this edge 2. This edge 2 is incident with vertices A and D, and edge 2 is said to connect to A, said to connect A and D. Okay, and so on and so forth. Now, let's have another definition. So the set of all neighbors of a vertex V of a graph consisting of vertices and edges is denoted by N of V. So the neighbors of a certain vertex may be may be denoted by N of V, and it is called as the neighborhood of V. So we can say here that the N of V will be consisted of the neighbors, or those that those vertices that are adjacent to this vertex na V. Okay, so we list it down into within a set. Now let's look at this vertex E. So what are the vertices that are adjacent to E? So these are vertices D, B, and C. Okay, or B, C, and D. So we can then say that these vertices are the neighborhood of the vertex E. Okay, so let's try to look at vertex A. So what would be the neighborhood of A? So N of A would be a set containing B and D. Okay, since B and D are adjacent to vertex A. Okay, now let's move on to another definition. So the degree of a vertex in an undirected graph is the number of edges that are incident with it, except that a loop at the vertex contributes to the degree of the vertex. So the degree of the vertex V is denoted by deg of V. Okay, so let's look at the same example. So how many vertices are adjacent to E? So there are 3. These are B, C, and then D. And since they are adjacent, it means that there are 3 edges that are incident with this vertex E. So if we count this out, this equals to 3. So we can then say that the degree of A is equal to 3. Okay, so let's have another example. So we have vertices or nodes A, B, C, D, G, E, and then F. And then while this graph is connected, the node G, on the other hand, is isolated or not connected to any of the other vertex in the graph. Okay, so what we are going to do here is determine the neighborhood as well as the vertex of as well as the degree of each vertex. Now let's start with vertex A. So the neighborhood of A is B and F. So we can then say that the degree of A is equal to 2. Okay, and then what about for the neighbors of B? The neighbors of B are A, F, C, and then E. And what are the number of edges that are incident to B? So it follows from the number of neighborhood that the degree should be equal to 4. Okay, so what about for letter vertex C? So vertex C is connected to B, D, E, and then F. So we can then say also that the degree is equal to 4. And for the vertex D, D is connected to only one vertex, which is C. So we can then say that the degree of D is 1. And for the vertex E is connected with C, B, and the F. And if we count all the edges that are incident with E, it is equal to 3. Okay? And for F is connected with A, B, C, and E. And the number of edges that are incident with F is equal to 4. Okay? And for G is not connected to any vertex in the graph. So we can say that its neighborhood is null and its degree G is equal to 0. Okay, and let's have this another example. So in this example, we have 5 nodes or vertices A, B, C, D, and E. And we can see that compared to the previous example, this one is a multi-graph since there are multiple edges that are connecting the same vertex. Let's say A and E are connected by two edges, and then E and D are connected by 3 edges. Okay, and there is also a loop. So rather than multi-graph, so this should be called pseudograph instead, since there is also a loop apart from the multiple edges. Okay, so now let us also determine the number of neighborhood as well as the degree of each vertex. Okay, let's start with vertex A. So the neighbors of vertex A are B, D, and then E. And what is the degree of A? So we simply have to count. So 1, 2, 3, and then 4. So the degree of A is equal to 4. And the degree of vertex V, on the other hand, is 6. So if we look at its neighbors, it has neighbors A, C, sorry, this should be C. A, C, D, and then E. Okay, so if we count this one, 1, 2, 3, 4, and then 5. So we have only 5 na edges that are incident with B. However, we must note that the loops must be counted twice. So we have to count this loop 2 times. So 1, 2, 3, 4, 5, and 6. So we can then say that the degree of B is 6. And its neighborhood is A, C, D, and then E. So what about for, let me just correct this. So let me remove, sorry, what did I remove? B here again. So now for C, C is connected with B only. And its degree is only 1. And for D, D is connected with B, E, as well as A. All right. So sorry for the bad color. So it was not fixed. So it is connected with B, A, and then E. And if we count the number of edges, it is 1, 2, 3, 4, and then 5. So we can then say that the degree of D is 5. And then for the vertex E is connected with A, B, and then D. So we can then say that A, B, D are the neighbors of E. And the degree is 1, 2, 3, 4, 5, and then 6. So it is equal to 6. Okay, so we are done with those examples. Let us move on with this, another theorem. So if we have a graph G consisting of vertices as well as edges, and it is an undirected graph with M number of edges, then we can say that twice the number of edges, that will be equal to the sum of all the degrees. So sum of the degrees of all the vertices. Okay, so in other words, the sum of the degrees is twice the number of edges. So let us try to understand that. Let us go back with this example. So we already discussed this in the previous slides, wherein this how we derive these neighbors as well as these degrees. Okay, so we don't have to repeat that again. So in the previous slide, we have said that twice the sum of all the degrees is twice the number of edges M. So how many edges do we have? We have 9. So if we count 1, 2, 3, 4, 5, 6, 7, 8, and then 9, right? And if we take the sum of all these degrees, it is equal to 18. Okay, so if we substitute these values to the equation, so we have 2 times 9, which is the number of edges. This will be equivalent, this summation will be equivalent to degree of A plus degree of B until degree of F. Okay, and we just have to substitute all of its values in this equation, take all of their sum, and it is equal to 18. And 2 times 9, or twice the number of edges, is also equal to 18. So we have proven this theorem. Okay, so in the next slide, next lecture, we are going to discuss about directed graphs.